Hello everyone, welcome to the class. In the last lecture, I described how the digital communication system is different from analog communication system and how the advantages of the digital communication system can be used to design a better system over the analog system. Now, what were the reasons why the digital communication system was preferred? The first reason was the noise immunity, and the second reason was the regenerative repeaters, that we can use the regenerative repeaters while the signal is traveling from the source to the destination. The repeaters can clean the noisy and distorted incoming signal and will regenerate the clean pulses, and those clean pulses will be transmitted further towards the destination. And we can place such repeaters along the path between the source and the destination. And almost all the communication systems being installed today are digital. Now, if we look at the regenerative repeaters for some time, what happens is this spreading of the waveform happens because of the impairments introduced by the channel. Now, and the waveform gets spreaded across the wider frequency range. Now, what the repeaters will do actually, the noise components outside the frequency band of the signal are removed. So these noise components in the outside of the desired frequency band will be removed. So in that case, what will happen? The noise components will be removed, and the signal to noise ratio in that case will increase. And in the desired band, using a band pass filter, we will be able to get the signal to noise ratio in that desired level where we can detect the incoming signal. All right, so that's the job of the regenerative repeaters. Now let us look at the frequency spectrum, because the signal ultimately will have to be occupied in the electromagnetic spectrum only. So how the electromagnetic spectrum plays an important role in defining the message signal, and then we will be using modulation to transform the signal from lower frequencies to the higher frequencies. Frequency spectrum allocation is the division of the electromagnetic spectrum into radio frequency bands. Now, the spectrum management is fully controlled and regulated by governments in most of the countries. Radio propagation has no boundaries. Radio propagation does not stop at normal boundaries. Due to technical and economic reasons, governments often sought to harmonize the allocation of RF bands and their standardization. Now, ITU, which is International Telecommunication Union, is a specialized agency of the United Nations that is responsible for issues that concern information and communication technologies. For example, they help in coordinating the shared global use of the radio spectrum, that how the radio spectrum will be allocated and used is actually governed by an international telecommunication union, which is an agency of the United Nations. It also promotes international cooperation in assigning satellite orbits, works to improve telecommunication infrastructure, and of course, the ITU, and there are other organizations also which assist in the development and the coordination of the worldwide technical standards, which actually govern how the telecommunication will happen in countries, in regions. Now, if you look at the electromagnetic spectrum, this is the EM frequencies, electromagnetic frequency spectrum from DC, from zero frequency to light and further beyond light also. Optical ranges are referred to by wavelength lambda is equal to c by f, where lambda is the wavelength and c is the velocity of light and f is the frequency of the wave. Now from this is the division that I have shown from 30 kilohertz to around 300 gigahertz. Will this range will form the radio waves, and so this is from 30 kilohertz to 300 gigahertz is the radio frequency range, whereas the range from 300 megahertz to say 300 gigahertz is the microwave range, right? So within which comes also the millimeter range, that is from around 30-40 gigahertz will be the millimeter range, which will actually be used in 5G communications, right? Okay. And these are some of the, and this actually diagram shows the application areas in the frequency bands. So this is an old actually picture which gives us an idea up to 300 gigahertz. Actually, the most of the wireless communication channels that exist at present go up to 5 or 6 gigahertz, right? Beyond that, the the frequency range comes under 5G communications. That is still under progress in many countries. The 5G has already been rolled out, and like China and other European countries, and they are doing the communication. They have installed the infrastructure for 5G communications also. Okay. Uh, these Now let us discuss about two fundamental um, characteristics which often the people get confused with. One is the channel bandwidth, the other is the signal bandwidth. Now, what is bandwidth actually? So bandwidth is a measure of the width of a range of frequencies from the minimum to the maximum frequency values, and it is measured in hertz. So bandwidth is the range um, from the lower frequency to the higher frequency. That means a band of frequencies will be there, which is the desired band, right? We will call that band as the bandwidth. All right. I will also explain once I will come to the analytical analysis. I will then explain that if we normalize the gain of the signal to, let us say, 1, then the signal will fall as the signal will travel a distance. Once the signal level reaches to 0.707 of the original strength, then you will see that you will get 2 points, two cutoff frequencies. One is the lower cutoff frequency of your desired band, the other will be the upper cutoff frequency of your desired band, and that range will be called as the bandwidth. Now, what is channel bandwidth? Channel bandwidth is a natural bandwidth which will be offered by the channel. So it is the range of signal bandwidths allowed by a communication channel without significant loss of energy. I mean, we cannot we will fix the attenuation levels. So within those attenuation levels, right? I mean, away on the beyond side of the attenuation level. That means the the signal strength has to be respectable. So the channel bandwidth is that bandwidth which is offered by the communication channel, so that the signals can travel through the channel, and the signal strength will not fall beyond a certain threshold value. So that will be called as the channel bandwidth, which is offered by the channel. All right. And what is actually the signal bandwidth? Signal bandwidth will be within which we place the signal. For example, if the signal is a baseband, if the let's say if the signal is a speech signal, the bandwidth of the speech signal is ranging from 300 hertz to 3400 hertz. So that is the signal bandwidth within which we place the information. Now that signal travels through the channel and how much bandwidth the channel offers to the signal, right? So that the respectable signal strength is achieved. If the audio, if you are sending the audio signal, and the signal bandwidth in that case will be from 20 hertz to 20 kilohertz. If it is a video signal, let's say, the signal bandwidth requirements can be from 0 hertz to 5 megahertz, right? So that is the signal bandwidth requirement, so that the complete information can come within those frequencies. Okay. Likewise, each signal also has a bandwidth B that measures the maximum range of its frequency components, which allows the signal to transmit with reasonable fidelity. This is constrained by the transmitter, right? Sometimes we can also band limit the signal, right? To so that we can meet the requirements of the sampling theorem. We all know that what is sampling theorem. The digital signal can be reconstructed back if the sampling that we are doing is at least twice the maximum frequency component present in the signal. So under the uh, practical scenario, we can band limit this signal so that it must serve our purpose as far as the quality of the communication is concerned, and we can band limit the signal so that we can choose a reasonable sampling rate so that we can do the perfect reconstruction of the signal. Now in continuous time signals, hz means number of cycles per second. That's a very basic concept. In discrete time signal, hz means number of samples per second, right? Number of samples. To understand the definition of the signal bandwidth, consider the speech signal which has a maximum frequency of 20 kilohertz. Actually, speech is band limited to 3400 hertz, maximum frequency component, whereas the audio frequency goes up to 20 kilohertz, right? So that becomes the bandwidth of a speech signal or an audio signal. Clear? So that is the signal bandwidth, and channel bandwidth is the bandwidth that the channel offers to the, so that the signal can travel smoothly through the channel, and it can produce a reasonable quality output. So channel and signal bandwidth. Now this is the speech spectrum for intelligibility applications. So this can be the frequency spectrum of the speech of the signal. So it is expected from up to 3400 hertz. The if you look at the relative power spectral density, so the if you go from 0 hertz to 3400, that is considered to be a reasonable frequency range, which can be used as a speech signal, so that the other person at the receiver end can recognize the voice of the speaker at the transmitter side. So this is considered to be a reasonable frequency range. So this is the complete spectrum of the speech signal. All right. Now these are some of the channel bandwidth requirements. So this, I mean, the channel must offer this much bandwidth, so that, because the signal is for example, let's take the case of a speech signal. It consists from the frequency components present in the speech signal are from 300 hertz to 3400 hertz. So if the channel is not offering a reasonable bandwidth, I mean, which covers this range, then the signal will be distorted. The channel will attenuate the signal to a great extent. So the channel bandwidth requirements for a telephone voice line is 4 kilohertz. Um, right? Copper pair offers a bandwidth of normally this offers 4 kilohertz. So this is the if this is the channel telephone voice line, the bandwidth offered by the channel is 4 kilohertz. Copper wires, unshielded or shielded twisted pairs, they offer a range from 1 to 600 megahertz, Cat 1 to Cat 7. These are the categories of the copper pair cables. Then coaxial cable offers a bandwidth of 500 megahertz, 6 megahertz channels. We can segregate the whole bandwidth. The 2.4 gigahertz radio frequency, it is 22 megahertz per channel. So 11 channels can be offered with this 2.4 gigahertz. If you use this frequency range, the wireless channel will offer 22 megahertz, 11 channels. And optical fiber is a channel, so it offers a great amount of bandwidth, that means in terahertz, so we can club many signals in this terahertz bandwidth which is offered by the channel. So I hope the things are pretty clear with the channel bandwidth and the signal band. These are two different terms. We should not confuse these two terms with each other. Okay, this is the same slide. This is the bandwidth requirement for a speech signal that I have already discussed. The faster a signal changes, the higher its maximum frequency, hence bandwidth. These are the characteristics of the signal which actually define the bandwidth of the of a signal. A signal rich in content, so if if the changes are faster, it will certainly involve a higher maximum frequency component. A signal rich in content that changes quickly have larger bandwidth than a signal that is dull or varies very slowly. So these are some of the characteristics which the engineer must know, by which if we choose a certain range of frequencies of the signal, right? So this content will be available within that bandwidth, right? For example, a high bandwidth, a battle scene in a movie, it can be very high. It can be a very high bandwidth signal. A video of sleeping animals, let's say, it can be a very low bandwidth signal. A signal can be successfully sent over a channel if the channel bandwidth exceeds the signal bandwidth. This is very important actually. A signal can be successfully sent over a channel if the channel bandwidth exceeds the signal bandwidth. It has to be more than this. If the channel is not offering the requisite amount of bandwidth to the signal which is having certain bandwidth, then the channel will distort the signal to a great extent. Whereas if the channel is offering a bandwidth which is exceeding the signal bandwidth, then signal can be occupied in that channel bandwidth. So channel will allow the signal to pass through it with the attenuation level within the desired attenuation levels. Now the signal power is related to the quality of transmission. Increasing signal power is what we are transmitting, right? How much power we are transmitting. This is very important because nowadays the systems are battery operated systems. We cannot transmit more power, right? The signal power PS is related to the quality of transmission. Increasing PS, of course, strengthens the signal pulse and reduces the effect of channel noise and interference. But increasing the signal power will also reduce the battery life of the devices. The channel bandwidth B and the signal power PS are exchangeable. One may use less bandwidth if willing to increase the power, or one may reduce the power if given a bigger bandwidth. So that trade-off can be done. The two primary communication resources are the bandwidth and the transmitted power. So you have to trade off between these two. Okay. In a given communication channel, one resource may be more available than the other. So that is um, that the engineer must know while designing a communication system. The excuse me. The examples that I'm taking is of a telephone channel or a space vehicle where the requirements can be different. Now let us come to the very important topic of modulation. Analog signal generated by the message source. Now, what is the source? A source can be, your whatever you are speaking, that you are a source of speech. The other can be, the other sources can be, for example, a text written on a page, that is the source of message, right? So, or the other example can be can be where the tele printer kind of thing, which is um, teletexting kind of things, which is generating the messages in the form of alphabets. Now the analog signal generated by the message source is called baseband signal. So it is called a baseband signal. Such a signal has low frequency components. Recall the speech spectrum shown above. Shown above means the other slides. Because that range is from 300 hertz to 3400. So that's a very low frequency signal. And that is known as a baseband signal. The baseband signals may be directly transmitted without modulation. What is modulation? Modulation is that transforming the signal, which is the baseband signal, to to a certain waveform, which to a certain waveform, other waveform. I mean, how you can regulate the signal. Either you can directly transmit the baseband signals without transforming or translating it to higher frequencies, right? Without modifying the natural frequencies of the signal. That will be known as the baseband modulation. So for audio telephone signal with approximately 3 kilohertz bandwidth is transmitted on twisted pair wire with almost the same bandwidth. However, baseband signals are not always suitable for direct transmission. When signal and channel frequencies do not match, channel cannot be moved. So channel cannot be moved. You have to translate the signal frequencies. So in this case, the signal must be moved to the right channel bandwidth. So if the signal is lying here, your channel provides you the bandwidth within this range. So the signal has to be translated to this portion. So here you need some kind of modulation. That means you need some kind of translation of the baseband signal frequencies to the channel bandwidth, wherever the channel is offering a bandwidth. So this is one of the need of modulation. Thus, the message signal must be modified for possible efficient transmission. This modification is called modulation. In the modulation process, the baseband signal modulates the carrier signal. So we take a higher frequency signal and we superimpose the baseband signal over the carrier signal. The carrier signal is a sinusoid of higher frequency. Through modulation, one parameter of the carrier signal CT, for example, one of the parameters we will pick from the carrier signal. So how many parameters the carrier signal have? How many parameters it has got? It has got 3 parameters: the amplitude, the frequency, or the phase. Now, one of the parameter is varied in accordance, is varied in proportion to the baseband message signal, MT. Right. Now, if we vary the amplitude of the carrier wave with respect to the message signal, right? message signal means the amplitude of the message, how the message is being represented. If you vary the amplitude of the carrier wave in accordance with that, so that will be called as the amplitude modulation in analog domain. If you vary the frequency, it will be known as the frequency modulation. If you vary the phase of the carrier wave, it will be known as the phase modulation. So these are the analog modulation schemes. Now, the uh, what is carrier signal? It is a deterministic signal because we are generating this signal. It's a deterministic signal. Modulating signal is a probabilistic or random signal because whatever the signal is coming from the source, it is probabilistic or random. And what the modulated signal becomes, it again becomes a probabilistic signal. These are some important characteristics one must understand. Remember that in communication system, we also have noise that is probabilistic. So noise is again probabilistic and random. Demodulation is a reverse process carried out at the receiver to recover the original baseband signal MP. Right. Now, the important reasons for modulation are one is the ease of transmission on radio waves, right? So that I have already explained you how it will be if the channel is offering a bandwidth in certain range, how you can translate the baseband frequencies to the bandwidth of the channel. And once you take the signal to once you use a carrier frequency of higher carrier, once you use a higher carrier frequency, then in that case you can multiplex many signals in that frequency range, right? So the higher frequency ranges can carry forward more signals, and that is known as the multiplexing of the signal. And we also know that the antenna height, the antenna requirement for the signal transmission is approximately equal to lambda by 4, right? So depending on the wavelength of the signal, the antenna height will be required. Now, if we use lower frequencies, right, antenna height will be in kilometers. But if we translate or modulate the message signal onto higher frequency carrier waves, in that case, the antenna height requirements come to the practical limits, right? So these are in terms of wavelengths, these are the uh, wavelengths of the different ranges of electromagnetic spectrum. All right, and the wavelength is given by C by F. Now, we know as I have described you, D is the wavelength lambda is inversely proportional to the frequency, right? If D is the antenna dimension, D is directly proportional to the wavelength. So higher the wavelength, higher the antenna dimensions required. Now, it is an example here. For a frequency signal of 100 hertz to 3 kilohertz, the wavelength is 100 kilometers. So if we take lambda by 4 of this, so 3000 approximately kilometers of antenna are required. But if we translate this signal to, let's say, 100 megahertz using a carrier frequency of 100 megahertz, in that case the antenna requirements will be only 3 meters, which is a very practical limit for uh, designing an antenna. So modulation becomes, if you want to transmit a signal to more distant places, you need to do the modulation, right? Where the antenna requirements will be uh, very much within the practical limits. So I have already explained what is multiplexing. Modulation allows multiple signals to be transmitted at the same time in the same geographical area. Consider TV signals without modulation. Multiple video signals will be interfering with each other because all video signals inherently have the same bandwidth of approximately 4.5 megahertz. If we do not translate the frequencies to the original TV frequencies to certain higher, if we do not modulate it, then the signals will interfere with each other. But if we modulate and translate the frequencies to higher range, we can use the frequency division multiplexing, and many signals can be transmitted through using the frequency division multiplexing. Right. FDM is the method of transmitting several signals simultaneously over non-overlapping frequency bands. Similar approach is used in the AM and FM radio broadcasting. Besides FDM, there is one more multiplexing technique which is called as the time division multiplexing. So within a time span, uh, every channel will be allocated time instants. So we can send samples from other signals here. So this is the if G1T is one signal, G2T is the other signal. So we can place sampling instants of G1T are this one and this one. So we can place the sampling instants of G2T, other signal, in between the sampling instants of G1T. So this is known as time division multiplexing. All right. So this we can also use. Now, important reasons for modulation I have already described. Modulation is the process to move the message signal into a specific frequency band dictated by the physical channel. AM and FM radios and old TV signals are based on analog modulation techniques. So we are in the era of at present we are in the era of 5G, but earlier it was 2G, 3G, and 4G. Those use all digital modulation techniques. So we will cover the digital modulation techniques also, and I will explain you about the digital modulation techniques in the next lecture. Thank you.